What if the universe we know today, with its dazzling galaxies, swirling nebulae, and vast cosmic tapestry, wasn't always this way? Picture a time when darkness ruled, when the very fabric of space underwent a transformation so profound, it rewrote the rules of existence itself. This isn't science fiction, it's the Cosmic Reionization Era, one of the most mysterious chapters in the story of our universe. A period so enigmatic, scientists are still piecing together its secrets, like detectives sifting through cosmic clues scattered across billions of years. And today, we're diving deep into 25 of its most baffling mysteries, each one a thread in the grand tapestry of how everything we see came to be. Think about the night sky, those pinpricks of light that have guided explorers, inspired poets, and sparked humanity's endless curiosity. But long before those stars shimmered into view, the universe was a shadowy void filled with a dense fog of hydrogen gas. Then something extraordinary happened. Over hundreds of millions of years, an invisible revolution unfolded as the first galaxies flickered to life, their fierce radiation burning away the cosmic gloom. This was reionization, a celestial metamorphosis that lit up the cosmos, sculpting it into the universe we recognize today. Yet, how exactly did this happen? What forces drove this dramatic change, and why do some pieces of this puzzle still refuse to fit? That's where the mystery deepens. Despite decades of research, the Cosmic Reionization Era remains a frontier of unanswered questions. Was it the work of massive stars blazing brief but brilliant lives, or did supermassive black holes lurking in the hearts of young galaxies play a hidden role? Even the timeline is a riddle. Did this transformation unfold smoothly, or in violent, uneven bursts? Every discovery seems to peel back another layer, revealing just how much we still don't know. So, if you've ever looked up at the stars and wondered how they came to be, you're about to embark on a journey to the edge of our understanding, where the universe's greatest secrets are still waiting to be uncovered. The universe's great awakening didn't happen by accident. Something had to tear apart the ancient sea of neutral hydrogen that filled the cosmos. But what? Even now, astronomers are locked in a heated debate over the trigger that sparked reionization. Some argue it was the birth of the first galaxies, their young, furious stars pumping out enough ultraviolet radiation to strip electrons from hydrogen atoms in a relentless wave. Others point to quasars, monstrous black holes at the centers of galaxies, devouring matter and spewing energy so intense it could have ionized gas across vast distances. Then there's the wild card. Could exotic, unknown particles or even the decay of dark matter have played a role? Just when we thought we were closing in on answers, the James Webb Space Telescope sent back data that turned everything upside down. It spotted galaxies from the reionization era that were smaller and fainter than expected, too feeble, some say, to have done the job alone. Yet there they were, existing earlier than models predicted, as if the universe had flipped the switch faster than anyone imagined. The puzzle only deepens when you consider pockets of hydrogen that resisted ionization far longer than they should have, leaving behind cosmic voids where the fog stubbornly clung. What if the truth lies in a combination of forces? Picture this. Galaxies lit the first sparks, but quasars fanned the flames, while some unseen phenomenon filled in the gaps. Or perhaps the process wasn't uniform at all, a chaotic patchwork of ionized bubbles, some growing fast, others lagging behind. The more we learn, the clearer it becomes. Reionization wasn't a single event, but a cosmic tug-of-war, a battle between light and shadow that shaped the universe we inhabit today. And with every new observation, we're reminded how much we still don't understand about the forces that sculpted the dawn of everything. One of the most baffling contradictions in the Cosmic Reionization Era isn't just what caused it, but when it happened. The universe didn't flip a switch and suddenly become transparent. Instead, this transformation rolled out like a chaotic, uneven storm, leaving behind a trail of conflicting evidence that has astronomers scratching their heads. Take distant quasars, for example, beacons of light from the early universe. Their spectra tell us that some regions were fully ionized as early as 800 million years after the Big Bang. But then there's the cosmic microwave background, the afterglow of the universe's birth, which suggests reionization dragged on for another 200 million years. That gap is wider than the entire age of Earth's dinosaurs, so what explains the mismatch? Some theories suggest the process was more like a patchwork quilt than a single sweeping wave. Imagine pockets of ionized gas bubbling up around early galaxies, while vast stretches of neutral hydrogen stubbornly held on, resisting the radiation blasting from young stars. Over time, these bubbles grew and merged, but not at the same speed everywhere. Perhaps dense regions of the universe cleared first, while more isolated corners took longer, like how sunlight scatters unevenly through a forest canopy. Another possibility, early quasars might have acted like cosmic blowtorches, carving out ionized tunnels in specific directions while leaving other areas untouched. But here's where it gets even stranger. The latest observations from deep space telescopes reveal galaxies that shouldn't have existed early enough to contribute to reionization, yet there they are, shining in the darkness. Did these faint, small galaxies pack an unexpected punch? Or was there something else at work, like hidden populations of even earlier stars, too dim for us to spot? The timing puzzle isn't just about dates on a cosmic calendar. It's a clue that our understanding of the universe's youth might be missing a crucial piece. And until we solve it, the story of how light triumphed over the cosmic fog remains frustratingly incomplete. But what if the architects of reionization weren't just made of the stuff we can see? Lurking in the shadows of this cosmic drama is dark matter, the invisible scaffolding of the universe, whose gravitational pull may have quietly shaped the entire reionization process. While dark matter doesn't emit or absorb light, its sheer dominance over cosmic structures suggests it could have been the unseen hand guiding the formation of the very galaxies that lit up the early universe. Here's how it might have worked. In the primordial cosmos, dark matter's gravity acted like a cosmic magnet, pulling ordinary hydrogen gas into dense clumps. Those clumps collapsed into the first proto-galaxies, creating the nurseries where stars could ignite. Without dark matter's invisible framework, galaxies might have formed too slowly or too sparsely to ionize the universe efficiently. Some simulations even suggest that regions rich in dark matter became hotspots of early star formation, blazing trails through the hydrogen fog faster than expected. Yet the plot thickens. A handful of theoretical physicists propose something far stranger. That dark matter itself might have decayed, releasing energy that directly contributed to reionization. This isn't mainstream science, it's a speculative but tantalizing idea. If certain exotic particles of dark matter were unstable, their breakdown could have produced bursts of radiation or fast-moving particles, adding another layer of chaos to the ionization process. Imagine billions of invisible particles vanishing in flashes of energy, each one a tiny spark in the cosmic dark. Of course, not everyone's convinced. Critics argue that conventional models of dark matter, cold, slow-moving, and inert, don't need this extra complexity to explain reionization. But with anomalies like those early, faint galaxies spotted by JWST, the door remains open to wilder possibilities. Whether as a silent architect or an active participant, dark matter's role in this epoch is far from settled. And that's what makes it one of reionization's most intriguing mysteries. While we know the first galaxies must have been the engines of reionization, there's a glaring problem. When we point our most powerful telescopes at the early universe, we don't find enough of them. This is the missing galaxies puzzle, and it's throwing a wrench into our understanding of cosmic history. If reionization required a staggering amount of ultraviolet radiation to strip electrons from all that hydrogen, where did the energy actually come from? Current models suggest we'd need millions of early galaxies working together to pull it off. Yet so far, even the James Webb Space Telescope, humanity's most advanced eye on the cosmos, has only found a fraction of what the math says should be there. One possibility is that these pioneer galaxies were simply too dim for us to detect. Imagine trying to spot a single candle from across an entire city. Now scale that up to cosmic distances and you get the challenge astronomers face. These early star factories might have been small and inefficient, burning their fuel slowly instead of in brilliant bursts. Their light, stretched and diluted by billions of years of cosmic expansion, could be vanishing into the noise of the universe's background glow. Some researchers suggest we're only seeing the brightest outliers, the cosmic equivalent of spotting skyscrapers, while missing whole neighborhoods of dimmer buildings. But there's a more unsettling alternative. What if our models are wrong? The calculations predicting how many galaxies should exist are based on assumptions about how quickly stars formed in the early universe. If those assumptions are off, say, if early stars were more massive and short-lived, pumping out far more ionizing radiation before exploding, then maybe fewer galaxies could have done the job. Or perhaps the first stars formed in ways we don't yet understand, clustering in unexpected patterns that left gaps in our observations. The most intriguing clue comes from the cosmic microwave background. Its faint polarization patterns hint that reionization might have started earlier than galaxy counts suggest, meaning something else, something we haven't seen yet, could have kicked off the process. Could there have been an earlier generation of stars, born and burned out so fast they left no visible traces? Or did black holes, voraciously feeding in the cores of protogalaxies, contribute more energy than we thought? Every unanswered question makes this mystery deeper. If the missing galaxies are just hiding in plain sight, future telescopes with even greater sensitivity might finally reveal them. But if they truly aren't there, we may be standing on the brink of rewriting cosmic history, discovering that the universe's greatest light show was fueled by something stranger than we ever imagined. Hidden within the light of distant quasars lies one of reionization's most perplexing clues, a ghostly fingerprint of hydrogen that shouldn't exist. When astronomers analyze quasar spectra, they expect to see a predictable pattern: the Lyman alpha forest, a series of absorption lines created as the quasar's light passes through clouds of neutral hydrogen. But something's off. Some of these clouds appear too dense, too stubborn, lingering long after reionization should have wiped them clean. It's as if patches of the ancient cosmic fog refuse to dissipate, clinging to existence like shadows in a sunlit room. The real shock came when scientists ran simulations to recreate these structures. No matter how they tweaked the parameters, adjusting the intensity of early starlight, the distribution of galaxies, even the behavior of dark matter, their models couldn't produce the intricate web of hydrogen clumps we actually observe. The universe, it seems, played by rules we haven't quite decoded. Some theorize these anomalies are cosmic fossils, regions where radiation from early stars simply didn't reach, leaving behind isolated pockets of neutrality. Others propose a more radical idea, that collapsing gas clouds, heated by their own gravitational energy, briefly recombined into neutral hydrogen before being torn apart again. Then there's the timing problem. The most baffling Lyman alpha features appear in quasars shining from an era when the universe was supposedly fully ionized. If neutral hydrogen survived that late, did reionization take far longer than we thought? Or could these be signs of a secondary process, perhaps cold streams of gas falling into galaxies, creating temporary hydrogen reservoirs? Every explanation raises new questions, and with each breakthrough, the Lyman alpha forest grows more enigmatic. What makes this mystery so tantalizing is its sheer persistence. These absorption lines aren't rare glitches, they're everywhere, etched into the light of countless quasars. It's as if the universe left us a deliberate trail of breadcrumbs, hinting at a hidden chapter in the story of reionization. And until we crack the code, these ghostly traces will remain one of cosmology's most haunting puzzles. What if the universe's great awakening wasn't a single, triumphant event, but a series of false starts with early attempts flickering out like matches in the wind? This is the startling possibility raised by radio telescopes peering back to the so-called cosmic dawn. Their data suggests that long before the final, decisive reionization, there may have been fleeting epochs where ionization began, only to collapse back into darkness. Imagine bubbles of ionized gas blooming in the primordial cosmos, their edges glowing with newborn starlight, then vanishing, swallowed once more by the hydrogen fog. The evidence comes from subtle ripples in the cosmic microwave background, combined with unexpected dips in radio waves detected by instruments like the hydrogen epoch of reionization array. These dips hint at moments when neutral hydrogen atoms absorbed radiation, only to re-emit it at specific frequencies, but the patterns don't align with a smooth, steady process. Instead, they point to episodic bursts of ionization, as if the universe was struggling to clear the fog, succeeding only after multiple attempts. Why would these early bubbles fail? One theory points to the fragility of the first stars. Unlike modern stars, which often form in metal-rich environments, the pioneers were made of pure hydrogen and helium, prone to burning hot and fast before exploding as supernova. Their violent deaths could have blown away nearby gas, starving subsequent star formation and snuffing out ionization in their vicinity. Another possibility involves the chaotic clustering of early galaxies. If they were too scattered, their radiation might have created isolated ionized pockets that couldn't merge, leaving vast neutral regions to reclaim the territory. But the most tantalizing idea is that dark matter played a role. In certain models, dark matter particles could have interacted with photons or neutrinos, subtly draining energy from the ionization fronts and causing them to stall. Picture a cosmic tug-of-war, light pushing, dark matter pulling, until the equilibrium tipped back toward darkness. The implications are profound. If reionization had false starts, it means the universe's transition to transparency wasn't inevitable. It was a precarious dance of physics, with moments where the cosmic scales nearly tipped the wrong way. And if some of those early ionization bubbles had persisted, the universe might have looked radically different today. Galaxies could have formed earlier in denser clusters, altering the entire architecture of the cosmos. This isn't just about filling in a timeline. It's about understanding how delicate the balance of reionization truly was. One failed attempt might leave traces we're only now learning to read, like echoes of a struggle buried in the static of deep space. And with every new radio telescope tuned to the cosmic dawn, we're listening harder, hoping to catch the whispers of those first faltering steps toward light. The universe's transition from darkness to light wasn't a clean break. It was a messy, overlapping dance of epochs, each one blurring into the next. Just as the first stars ignited, ending the so-called Dark Ages, reionization began its slow burn, leaving astronomers with a cosmic detective story where the clues are hopelessly entangled. Imagine trying to listen to 3 songs playing at once, each from a different era, and struggling to pick out a single melody. That's the challenge scientists face when probing this pivotal moment in cosmic history. Take the faint radio whispers from neutral hydrogen, the telltale signature of the Dark Ages. These signals should fade as reionization progresses, replaced by the ultraviolet glow of newborn galaxies. But the reality isn't so neat. In some regions, the two signals overlap, as if the universe couldn't decide whether to cling to the old darkness or embrace the new light. The culprit, the first stars themselves. These pioneers didn't just illuminate the cosmos, they also polluted it with heavy elements when they exploded, altering how subsequent starlight interacted with surrounding gas. The very act of ending the Dark Ages set the stage for reionization, weaving the two epochs into an inseparable tapestry. Then there's the problem of timing. Reionization didn't wait for the Dark Ages to fully end before making its move. In denser regions, galaxies clustered early, ionizing their surroundings while more remote areas languished in neutrality. This patchwork effect means that for hundreds of millions of years, the universe was a bizarre hybrid, part ancient fog, part modern clarity. Telescopes peering back to this era catch glimpses of both, dark, starless voids existing alongside brilliant young galaxies, like shadows and spotlights sharing the same stage. Adding to the confusion, the tools we use to study these epochs often pick up blended signals. The Lyman alpha forest, that fingerprint of hydrogen absorption in quasar light, records not just reionization's progress, but also the aftermath of the first supernova, which stripped electrons from atoms in unpredictable ways. Even the cosmic microwave background, our snapshot of the infant universe, carries imprints of both the Dark Ages' end and reionization's dawn, smeared together by billions of years of cosmic expansion. The deeper we look, the clearer it becomes. These cosmic chapters weren't sequential but concurrent, each influencing the other in ways we're only beginning to untangle. Maybe reionization didn't have a single starting gun, just a gradual, chaotic shift where darkness and light wrestled for dominance, leaving behind a universe forever changed by their struggle. If the Cosmic Reionization Era had a pattern, it wasn't the orderly sweep of sunlight at dawn. It was more like a flickering neon sign buzzing to life in unpredictable patches. Some corners of the universe became transparent in a cosmic blink, while others clung to their primordial haze for hundreds of millions of years longer. This unevenness isn't just a quirk, it's a direct challenge to the assumption that reionization unfolded as a smooth, uniform wave. The clues come from painstaking maps of hydrogen density across the early cosmos. By studying how light from distant quasars filters through ancient gas clouds, astronomers can reconstruct the distribution of neutral hydrogen like a cosmic weather map. What they've found is staggeringly complex, vast ionized voids bordered by stubborn filaments of lingering fog, with no clear rhyme or reason to their arrangement. Some regions the size of modern galaxy clusters cleared out shockingly fast, while others seemed almost resistant to change, as if shielded by some invisible force. One leading theory points to the universe's own lumpy beginnings. Tiny density fluctuations from the Big Bang imprinted in the cosmic microwave background meant matter wasn't spread evenly. Where gas clumped together more densely, galaxies formed earlier and in greater numbers, their collective radiation blasting away local hydrogen like a stellar wind clearing dust. But in sparser regions, fewer stars meant weaker ionization, leaving behind islands of neutrality. Imagine pouring water over a bumpy sidewalk. Puddles gather in the dips while higher spots dry instantly. Yet there's a catch. Some high-density areas reionized later than expected, while certain cosmic backwaters cleared suspiciously early. This can't be explained by galaxy counts alone. Could black holes have played an outsized role? Quasars, the blazing cores of galaxies with voracious supermassive black holes, emit torrents of ionizing radiation, but their placement seems almost random in the early universe. A single quasar might have carved an ionized tunnel billions of light years long, while neighboring regions languished in darkness. Another puzzle comes from the cosmic microwave background's polarization patterns. These subtle swirls suggest some ionization bubbles grew far larger than standard models predict, as if an unknown amplifier supercharged their expansion. Some theorists speculate that dark matter's gravitational pull might have funneled gas into concentrated streams, creating hyper-efficient ionization fronts. Others wonder if exotic physics like primordial magnetic fields could have reshaped the fog's behavior. The most intriguing anomalies are the so-called reionization relics, pockets of hydrogen that survived well into the era of modern galaxies. One such region, discovered near the galaxy NGC 4891, remained neutral until roughly 2 billion years after the Big Bang, a cosmic holdout defying all explanations. Was it shielded by an early magnetic field? Did it float in a void too vast for nearby starlight to penetrate? Or was there something fundamentally different about the hydrogen there? Every fluctuation in the fog is a clue not just to how reionization happened, but to the universe's underlying architecture. The variations suggest a cosmos far more dynamic and chaotic than our cleanest theories predict, where chance played as much a role as physics in shaping the dawn of light. And until we understand why some corners of the young universe stubbornly refuse to change, the story of reionization will remain tantalizingly incomplete. Quasars should be the rock stars of the reionization era, blazing beacons so bright they outshine entire galaxies. But here's the catch: according to everything we know about black hole growth, they shouldn't have had time to become that powerful so soon after the Big Bang. Yet the universe loves a paradox, and the phantom quasar paradox is one of its most baffling. These cosmic anomalies, spotted shining from as early as 670 million years after the universe's birth, flaunt energies that defy conventional timeline. How did supermassive black holes, which typically need billions of years to bulk up, reach such monstrous sizes in what was practically a cosmic blink? One explanation could rewrite the rules of black hole formation. Maybe the first black holes didn't grow slowly by nibbling on gas. They were born obese, collapsing directly from gigantic primordial gas clouds into 100,000 solar mass monsters. This direct collapse scenario bypasses the usual star-sized black hole stage, jump-starting growth before galaxies even finished assembling. It's like finding a skyscraper in the middle of a construction site, something skipped ahead of schedule. But even this theory strains under scrutiny. For these quasars to shine so fiercely, they'd need a non-stop buffet of matter, yet simulations struggle to explain how enough gas could funnel into their cores so efficiently in the sparse early universe. Then there's the eerie uniformity of their light. Some phantom quasars flicker with a regularity that suggests their accretion disks, the swirling rings of doomed matter, were strangely stable for such chaotic times. Modern quasars often sputter and flare as they consume material unevenly, but these ancient ones burn with an almost mechanical precision. Could magnetic fields, stronger in the early cosmos, have kept their feeding smooth? Or was there some exotic fuel source we haven't considered, like dense dark matter annihilating itself within their grasp? The real curveball came when astronomers noticed these quasars weren't just bright, they were too bright. Their spectra show ionized helium signatures indicating ultraviolet radiation so intense it shouldn't have been possible without overheating their own disk. It's as if these objects had cosmic afterburners, some extra energy source beyond simple gravity. That's led a handful of theorists down a wilder path. Perhaps phantom quasars tapped into primordial energy left over from the Big Bang itself, or even leaked power from hidden dimensions. But before we rewrite physics, there's a simpler, if unsettling, possibility. What if these quasars aren't outliers at all, but signposts pointing to a flaw in our cosmic calendar? Current methods for dating the early universe rely on measuring redshift, how much light stretches as space expands. But if certain regions expanded faster than others due to uneven dark energy distribution, objects there might appear older than they truly are. A quasar thought to exist at redshift 7 might actually be closer, its light distorted by pockets of warped spacetime. The paradox cuts to the heart of reionization itself. If phantom quasars were more common than we thought, their blistering radiation could have jump-started ionization in vast regions, leaving galaxies to finish the job. Or perhaps they were cosmic lighthouses, their beams carving ionized tunnels through the hydrogen fog, creating pathways for light to escape where stars alone couldn't. Either way, their existence hints at a universe far more inventive and far less predictable than our textbooks dare to suggest. Here's the problem with reionization. When you tally up all the ultraviolet radiation pouring out of early stars, there's a glaring gap in the cosmic budget. The math simply doesn't add up. To rip electrons from every hydrogen atom in the universe, you'd need an almost unimaginable amount of UV light, enough to outshine 100 billion suns for hundreds of millions of years. But when astronomers count up the known sources from that era, the faint galaxies spotted by the James Webb Space Telescope, the brilliant quasars blazing in the darkness, they come up short. By some estimates, we're missing nearly half the energy required to explain the universe's transformation. So where did the rest come from? One possibility is that we're underestimating the power of supermassive black holes. While quasars steal the spotlight, their quieter cousins, growing black holes in smaller galaxies, might have been stealth contributors. These hidden monsters, buried in dusty cocoons, could have pumped out UV radiation without the fanfare of their brighter relatives. Imagine thousands of these faint, voracious black holes scattered across the early cosmos, each one a silent factory of ionizing energy. Recent simulations suggest that if even a fraction of early galaxies harbored such black holes, their combined output might plug the radiation gap. Then there's the wild card, dark stars, not the glamorous pop icon, but hypothetical stellar behemoths fueled by dark matter annihilation. In the dense early universe, these theoretical stars could have formed with dark matter at their cores, releasing energy as exotic particles collided and decayed. Unlike normal stars, which fuse hydrogen, dark stars might have burned cooler but far longer, shining with a steady UV glow for millions of years. If they existed, their collective radiation could have been the missing piece in reionization's energy puzzle. The catch: no one's ever seen one. The plot thickens when you consider the escape problem. Even if early stars produced enough UV light, much of it might have been trapped by the thick hydrogen fog surrounding young galaxies. Only a fraction of that radiation would have leaked out to ionize the wider cosmos. Unless, that is, something helped punch holes in the gas. That's where supernovae come in, the violent deaths of massive stars. Their shockwaves could have blasted tunnels through the gas, creating escape routes for UV photons. But even that might not be enough. Perhaps the answer isn't one missing source, but a combination of overlooked contributors: faint black holes, dark stars, supernova-boosted photon escape, and even exotic particles we haven't discovered yet. Or maybe the universe found efficiencies we haven't imagined, recycling radiation in ways that left no trace. Until we solve this shortfall, reionization remains a cosmic enigma, a light show with half its bulbs unaccounted for. Helium, the silent partner in the cosmic reionization story, played by its own rules. While hydrogen stole the spotlight by becoming transparent first, helium stubbornly clung to its electrons, resisting ionization until the universe was nearly 1 billion years old. This delay wasn't just a cosmic quirk. It was a clue revealing hidden chapters about the growth of galaxies and the brutal evolution of the early cosmos. Here's why helium lagged behind. Ripping electrons from helium atoms takes far more energy than doing the same to hydrogen. Hydrogen's single electron gives up easily when hit by ultraviolet photons with just enough punch, what astronomers call Lyman continuum radiation. But helium's 2 electrons are bound tighter, especially the second one. To strip that away, you need photons with much higher energy, deep in the extreme ultraviolet or even soft X-ray range. Think of it like trying to pry open a locked door. Hydrogen's door might yield to a firm shove, but helium's requires a battering ram. That's where the mystery deepens. For helium to finally ionize, the universe needed galaxies mature enough to produce those harder photons. But early galaxies were small and their stars relatively cool, lacking the firepower to crack helium's defenses. Only later, as galaxies grew more massive, did their stars grow hotter and their black holes more frenzied, finally unleashing the torrent of hard UV needed? The timeline tells us something profound. Helium's reionization was a galactic coming-of-age story, a signpost marking when the universe's first structures reached a new level of cosmic violence. Yet the plot thickens when we look at the data. Quasars, those brilliant beacons powered by supermassive black holes, were once thought to be the primary drivers of helium reionization. Their fierce radiation certainly had the energy to do the job, but recent observations suggest something surprising. The bulk of helium's ionization happened before quasars became common enough to shoulder the blame. That leaves astronomers scrambling to identify other culprits. One leading candidate, the deaths of massive stars. When these giants exploded as supernova, their shockwaves could have heated surrounding gas to extreme temperatures, producing X-rays that gnawed away at helium's defenses. Another possibility is the collective fury of countless smaller galaxies, their combined output of hard UV photons adding up over time. Simulations show that as galaxies merged and grew denser, their radiation fields became harsher, like a roaring crowd drowning out a whisper. But here's the twist: helium didn't ionize uniformly either. Some regions of the cosmos, particularly near dense clusters of galaxies, cleared early, while more isolated pockets held out for hundreds of millions of years. This patchiness suggests helium reionization wasn't a single event, but a drawn-out campaign, with different cosmic forces taking the lead at different times. It's as if the universe had to assemble an entire toolkit: hot stars, black holes, supernova, before it could finally finish the job. The delay in helium's ionization isn't just a footnote. It's a cosmic fingerprint, revealing how galaxies evolved from modest beginnings into the radiant powerhouses we see today. And it hints at something even deeper. The universe's light didn't switch on all at once, but in layers, each one uncovering a new chapter in the story of how darkness gave way to brilliance. The cosmic web, a vast, invisible skeleton of dark matter and gas filaments connecting galaxies across the universe, might have been reionization's secret architect. While stars and quasars provided the radiation, the web's intricate structure could have acted as a cosmic plumbing system, channeling that light across unimaginable distances with eerie efficiency. Picture a network of highways carved through the primordial fog, where ionizing photons raced along filaments like commuters taking the fastest route home. Simulations reveal something astonishing. These filaments didn't just passively link galaxies, they amplified reionization's reach. Dense strands of hydrogen gas, pulled taut by gravity, became conduits for radiation. When a galaxy at a filament center ignited, its UV light didn't spill outward in all directions like a dimming bulb. Instead, the surrounding gas funneled photons along the filament's length, creating ionization tunnels that stretched tens of millions of light years. It's as if the universe itself conspired to spread the light, building roads for photons in the dark. But here's where it gets stranger. The cosmic web didn't just transport light, it shaped where reionization happened first. Regions where filaments intersected, known as cosmic nodes, became hotspots of early ionization. Galaxies clustered there benefited from a feedback loop. Their combined radiation traveled farther along the web, clearing gas faster and attracting even more galaxies to settle along these brightening thoroughfares. Meanwhile, isolated galaxies off the main filament struggled to make headway, their photons swallowed by the dense fog around them. This could explain why reionization unfolded in such a patchwork pattern, why some regions blinked transparent while others lingered in shadow. The most compelling evidence comes from supercomputer models that track photon trajectories during reionization. These simulations show photons zigzagging along filaments, bouncing from gas cloud to gas cloud like pinballs rather than traveling in straight lines. Some photons even surfed shockwaves from galaxy collisions, riding bursts of energy deeper into neutral territory. Astonishingly, a single photon could have helped ionize multiple patches of hydrogen along its winding path, stretching its impact far beyond what simple distance would allow. Yet mysteries remain. Why did some filaments transmit radiation better than others? Were certain strands primed by earlier cosmic events, their hydrogen already partially heated or stirred by ancient turbulence? Or did magnetic fields woven into the web's structure guide photons like rails guiding a train? The answers could redefine our understanding of how structure and light co-evolved in the early universe. One thing's certain, the cosmic web wasn't just a backdrop for reionization. It was an active participant, shaping the universe's transformation in ways we're only beginning to grasp. And if future telescopes can map these ionization highways in detail, we might finally unravel how darkness gave way to light, one filament at a time. The first stars in the universe weren't just different, they were cosmic anomalies burning with a purity we'll never see again. Born from nothing but hydrogen and helium, these so-called population 3 stars were the universe's original giants, potentially hundreds of times more massive than our Sun and blazing with violet fury. Their extreme temperatures would have made them ultraviolet factories, pumping out the precise radiation needed to rip electrons from hydrogen atoms and kickstart reionization. Yet for all their theoretical importance, these stellar pioneers remain ghostly figures in our telescopes, elusive, unconfirmed, and maddeningly absent from the very era they're supposed to define. The James Webb Space Telescope was supposed to change that. Designed to peer further back in time than any instrument before it, JWST infrared eyes were poised to finally capture the faint glow of population 3 stars or their explosive deaths. But years into its mission, the evidence remains circumstantial at best. Deep field images reveal plenty of early galaxies, some shockingly mature for their age, but no smoking gun signatures of metal-free stars. No telltale spectra with the distinctive fingerprints of pure hydrogen-helium fusion. No supernova remnants lacking heavy elements. It's as if the universe's first light bulbs vanished without a trace. So where did they go? One possibility is that population 3 stars were simply too fleeting to catch. With lifespans measured in mere millions of years, a cosmic blink. They might have formed, burned, and exploded before even JWST deepest gazes could register them. Their deaths would have seeded the cosmos with the first heavy elements, contaminating later generations of stars and erasing the pristine conditions they emerged from. Imagine trying to photograph a firework's initial spark. By the time your shutter opens, it's already faded to smoke, but there's a stranger twist. Some simulations suggest these stars might not have been the towering behemoths we envisioned. Instead of forming in isolation, they could have clustered in tight groups, their radiation pushing against each other and limiting their growth. These smaller, more numerous population 3 stars would still have produced ample UV light for reionization, but their fainter, scattered signatures would blend into the background of early galaxies, hiding in plain sight. The most tantalizing and controversial clue lies in a handful of distant galaxies spotted by JWST that appear too bright too early. Their light profiles don't quite match models of normal star formation. Could these be the nurseries where population 3 stars briefly shone? Or are we seeing the aftermath of their cataclysmic demises, supernova so powerful they outshone entire galaxies? The data is still fuzzy, but one thing's clear. If these stars were the engines of reionization, they left behind a puzzle with pieces that refuse to fit. And until we find definitive proof, the myth of the universe's first stars will remain just that, a brilliant hypothesis shining in the dark of our uncertainty. Deep in the static of the universe's oldest light hides a whisper, a faint radio signal at 21 centimeters, the precise wavelength emitted by neutral hydrogen as it spins in the cold void. This signal, predicted to carry echoes of the cosmic dawn, should be our Rosetta Stone for decoding reionization's earliest moments. But there's one problem: no one can agree if we've actually heard it. Some teams swear they've detected its faint hum, a cosmic murmur from 13.8 billion years ago. Others insist it's just noise, radio interference, instrument glitches, or wishful thinking amplified into false discovery. The controversy erupted in 2018 when astronomers using the experiment to detect the global epoch of reionization signature, or edges, announced they'd spotted the 21-centimeter signal's telltale dip in radio static. The shape was textbook, a shallow trough in the data, suggesting hydrogen atoms absorbing background radiation as the first stars flickered to life. But the signal was far stronger than any model predicted, almost twice as deep as theorists expected. That discrepancy threw the entire field into chaos. If the detection was real, it meant our understanding of hydrogen's behavior in the early universe was missing something fundamental. Perhaps the gas was colder than thought, or the cosmic microwave background hotter. Or worse, maybe undiscovered physics was at play, like interactions between dark matter and hydrogen that siphoned away thermal energy, deepening the signal beyond natural limits. Skeptics pounced immediately. The EDGE's antenna, parked in remote Western Australia to avoid human radio pollution, might still have picked up interference from aircraft, satellites, or even the telescope's own electronics. Other groups tried to replicate the finding with different instruments, like the Large Aperture Experiment to detect the dark ages and the shaped antenna measurement of the background radio spectrum. Their results: silence, no matching dip, no smoking gun. The 21-centimeter signal remained stubbornly elusive, leaving astronomers divided between those convinced they'd glimpsed the universe's birth cry and those dismissing it as cosmic static masquerading as meaning. The stakes couldn't be higher. If the EDGE's signal is genuine, it suggests reionization began earlier and more violently than models predict, with the first stars igniting by 180 million years after the Big Bang. That timeline would force a rewrite of galaxy formation theories, compressing the dark ages into a narrower window. But if it's an artifact, we're back to square one, left with only indirect clues to reconstruct an era that predates every galaxy, every quasar, every known beacon in the cosmos. New experiments aim to settle the debate. Next-generation radio arrays like the Hydrogen Epoch of Reionization Array and the upcoming Square Kilometer Array promise unprecedented sensitivity. Unlike single antennas like EDGE's, these sprawling networks can distinguish true cosmic signals from local interference by comparing data across dozens of receivers. They'll also map the signal's fluctuations in space, not just time, revealing how reionization's firestorms spread through the hydrogen fog. Until then, the 21-centimeter controversy stands as a cautionary tale, a reminder that even the universe's clearest signals can be lost in the noise of our own limitations. And buried in that uncertainty is a thrilling possibility that the answer, when it finally comes, might rewrite not just the story of reionization, but the laws of physics themselves. The universe seems to have a habit of hiding its smallest actors, those faint dwarf galaxies that should swarm around larger ones like fireflies around a lantern. According to our best models of cosmic structure, thousands of these tiny galaxies should orbit the Milky Way and its neighbors, relics of the chaotic early universe. Yet we've found only a fraction of them. This is the infamous missing satellites problem, and it might hold an unexpected key to unraveling reionization's biggest secrets. Here's the twist: these overlooked dwarfs could have been the unsung heroes of cosmic dawn. While titanic galaxies hog the spotlight, their smaller cousins might have done the heavy lifting in ionizing the universe's hydrogen fog. Picture this: a swarm of faint, hyperactive dwarfs, each pumping out UV radiation at rates disproportionate to their size. Their collective output could have been staggering, like 1,000 matches burning brighter together than a single bonfire. But why would these tiny galaxies be such efficient UV factories? The answer lies in their chaotic youth. Without heavy elements to regulate star formation, early dwarfs might have birthed stars in frenzied bursts, their short-lived massive stars flooding space with ionizing photons before exploding as supernova. That's where the mystery deepens. If these galaxies were so crucial, why can't we find more of them today? One possibility is brutally simple: they burned out. Unlike modern dwarfs, which chug along at a leisurely pace, the reionization era versions might have exhausted their gas supplies in just a few furious generations of star formation. Their fleeting brilliance would have left behind only dark, starless husks, invisible ghosts haunting the cosmic web. Another clue comes from their environment. Intense UV radiation from neighboring galaxies could have stripped these dwarfs of their gas, starving them before they could grow. It's like trying to light a candle in a hurricane. Some flames just couldn't last. But the real plot twist: we might have been looking in the wrong places. Traditional surveys hunt for dwarf galaxies by their starlight, but the most influential ones during reionization could have been cloaked in thick hydrogen clouds, their visible light smothered while their UV photons leaked out. Recent simulations suggest these dark dwarfs might have outnumbered the visible ones, their radiation stealthily sculpting the cosmos without leaving a trace. The James Webb Space Telescope is now peering into these shadows, searching for infrared signatures of their ancient star-forming fury. The implications are profound. If faint, forgotten galaxies played a starring role in reionization, it would rewrite the cosmic power rankings, proving that the universe's greatest transformations aren't always driven by its brightest beacons. Sometimes history is written by the smallest voices, echoing across billions of years. And if we ever solve the mystery of the missing satellites, we might finally understand how a universe cloaked in darkness found its way to light. The universe's great ionization event didn't just light up the cosmos, it left behind a hidden thermal footprint, a ghostly warmth lingering in the sparse gas between galaxies. But when astronomers finally measured the temperature of this intergalactic medium, they stumbled into a paradox. The gas wasn't as hot as it should have been. According to every simulation, the fierce ultraviolet radiation that tore electrons from hydrogen atoms would have superheated the gas, leaving it scorching for billions of years. Yet the real data tells a different story, like finding a campfire that burned white hot but left only lukewarm embers. This mismatch isn't just a minor discrepancy, it's a clue that something fundamental is missing from our understanding of reionization's aftermath. One leading theory points to cosmic expansion as the silent coolant. As the universe stretched, the gas might have thinned and cooled faster than expected, like steam dissipating in an ever-widening vent. But the math still doesn't quite add up. Another possibility involves an invisible cosmic refrigerator, dark matter. If certain exotic particles interacted weakly with the gas, they could have siphoned away heat without leaving a trace. Imagine an ice cube melting in a drink, cooling it but vanishing without bubbles or swirls to mark its passage. Then there's the wild card quantum cooling. Some theorists speculate that in the extreme conditions of the early universe, hydrogen atoms might have shed energy through exotic quantum processes we haven't yet observed in labs. Picture a crowd of excited electrons calming down not by bumping into each other, but by some strange subatomic choreography that lets them collectively forget their heat. It's a long shot, but the numbers tease at something unexplained. The most tantalizing evidence comes from quasar spectra. The absorption lines in their light reveal pockets of gas that cooled too fast, as if cosmic air conditioning kicked on in specific regions. Was this uneven cooling due to differences in galaxy density? Or did magnetic fields woven through the intergalactic medium channel heat away like veins carrying thermal blood? The answer could rewrite how we model galaxy formation. If gas cooled faster than we thought, the first stars and galaxies might have coalesced earlier, reshaping the entire timeline of cosmic dawn. It's like discovering that a race we thought lasted hours actually finished in minutes, forcing us to rethink every stride the runners took. And until we solve this thermal riddle, the true story of how the universe warmed up, then cooled down, will remain one of reionization's most puzzling chapters. Hidden in the faintest glow of the night sky, far beyond what our eyes can see, lies a cosmic whisper. It's the cosmic infrared background, an ethereal haze of light bathing the universe, and it might just hold the secrets of reionization's untold story. Unlike the brilliant galaxies or blazing quasars that dominate our telescopes, this glow is subtle, uniform, almost ghostly. But within its delicate patterns, astronomers have detected anomalies, tiny fluctuations like ripples on a pond that shouldn't exist if the light came solely from known sources. Could these be echoes of the universe's fiery transformation, lingering like cosmic breadcrumbs from the era when darkness gave way to light? The mystery starts with a simple question: where does this infrared light actually come from? At first glance, the answer seems obvious: countless distant galaxies, their starlight stretched and reddened by the expansion of the universe, blending into a diffuse backdrop. But when researchers meticulously subtracted the light from every known galaxy, the background refused to vanish. A stubborn excess remained, glowing stubbornly in the data. This unresolved infrared light is too smooth to be explained by ordinary galaxies alone, hinting at something stranger. Some argue it's the collective glow of trillions of faint, never-seen dwarf galaxies, their contributions too dim to pick out individually but overwhelming in some. Others whisper about more exotic possibilities: primordial black holes evaporating in bursts of radiation, or even the faint afterglow of dark matter particles annihilating one another in the void. The plot thickens when we zoom in on the infrared background structure. Its fluctuations don't match predictions based on galaxy counts. Instead, they show odd clustering, as if something else, something ancient and widespread, imprinted its signature on the light. One tantalizing theory points to the first stars, not as individual points of light, but as a seething, universe-wide population. Their combined radiation, absorbed and re-emitted by clouds of primordial dust, could have created a lingering infrared fog. Picture a cosmic echo chamber where the energy of reionization bounced between gas and dust for eons before finally reaching us, stretched and diluted but never entirely gone. Yet there's a wrinkle. Dust requires heavy elements to form, and heavy elements didn't exist until after the first stars had already died. So how could they have left an infrared signature? Unless, that is, those stars died violently, seeding their surroundings with ashes in time for the next generation to illuminate them. It's a cosmic catch-22, one that has led others to suggest that the infrared background's fluctuations might not be from stars at all, but from the chaotic birth cries of the universe's first black holes. As these black holes formed and grew, their accretion disks could have heated surrounding dust to infrared brilliance, creating a flickering tapestry of light woven into the fabric of space itself. The debate rages on, but one thing's clear: if we can decode the cosmic infrared background's riddles, we might finally glimpse the true architects of reionization. Not just the brightest beacons, but the countless forgotten sparks that together set the universe ablaze. And with every new infrared telescope probing deeper into this ghostly glow, we're closer to hearing the universe's oldest story, written not in stars or galaxies, but in the faint, warm afterglow of creation. What if reionization wasn't a one-time event, but two? A growing faction of astronomers is challenging the textbook narrative with a bold idea. The universe didn't transition from darkness to light in a single, sweeping revolution. Instead, it flickered first, lighting up with the violent births and deaths of population 3 stars, only to fade back into darkness before galaxies reignited the cosmos for good. This double reionization theory isn't just a wild hypothesis. It could explain some of the universe's most puzzling chemical contradictions. The clues start with helium. Mapping its distribution across the cosmos reveals strange pockets where this element seems too abundant, as if it had been cooked twice, first in the furnaces of those early, massive stars, then later by the radiation of galaxies. Intriguingly, the James Webb Space Telescope has spotted regions where helium appears enriched beyond what standard models predict, like cosmic leftovers from an earlier, forgotten feast. If population 3 stars briefly ionized the universe before winking out, their supernova would have scattered helium like celestial graffiti, leaving behind chemical breadcrumbs for later epochs to find. Then there's the timeline conundrum. Certain quasars shining from just 200 million years after the Big Bang show signs of ionized gas far earlier than mainstream reionization models allow. But what if this wasn't the main event? Imagine a false start where population 3 stars, burning furious and fast, cleared small bubbles of hydrogen before their explosive deaths ended the experiment. The universe would have slumped back into neutrality, its brief flirtation with light erased until galaxies, forming more slowly but enduringly, finished the job millions of years later. The most tantalizing support comes from the cosmic microwave background's polarization patterns. Subtle swirls in this ancient light hint at multiple ionization epochs, like layers of paint on a cosmic canvas. If confirmed, it would mean our universe didn't wake up once, it hit the snooze button, drifting back into darkness before truly rising to light. Of course, skeptics argue this theory overcomplicates the story. Maybe helium anomalies stem from overlooked galactic processes or quirks in how radiation traveled through the early cosmos. Yet for those who dare to question the single reionization narrative, the universe's history suddenly becomes far richer, a tale not of dawn breaking, but of a twilight interlude between 2 cosmic days. Black holes in the early universe were cosmic paradoxes, engines of destruction and creation, simultaneously fueling reionization while threatening to snuff it out. Picture a supermassive black hole at the heart of a young galaxy, devouring gas at a frenzied pace. As matter spirals inward, friction heats it to millions of degrees, transforming the black hole's surroundings into a blowtorch of X-rays and ultraviolet radiation. This energy could have carved vast ionized bubbles in the hydrogen fog, acting as cosmic clearings where light traveled freely. But here's the twist. Those same black holes often fired jets of plasma at near light speed, blasting gas far beyond their host galaxy's gas that might otherwise have cooled and formed new stars. In this push and pull, black holes weren't just passive players in reionization. They were frenetic conductors, alternately accelerating and slamming the brakes on the universe's transformation. The debate hinges on a simple question. Did black holes contribute more radiation than they suppressed star formation? Observations of early quasars suggest their ionizing output was colossal. A single quasar could outshine its entire galaxy by 1,000 times, its radiation reaching distances comparable to modern galaxy clusters, yet simulations tell a murkier story. When black hole jets plow through gas clouds, they don't just heat the material, they hurl it into the void, starving future generations of stars. Some models show galaxies near quasars stunted in growth, their gas reservoirs depleted before they could birth enough stars to sustain reionization. It's like a wildfire that clears the forest but leaves no seeds behind. Then there's the numbers problem. If black holes were reionization's heavy lifters, we'd expect to find far more of them in the early universe than current surveys reveal. The James Webb Space Telescope has spotted dozens of quasars from the reionization era. Impressive, but still too few to explain the ionization levels we detect. Unless, that is, most early black holes were hidden, dust-shrouded monsters veiled by thick gas clouds might have pumped out radiation without the telltale brilliance of quasars. Recent infrared detections of faint, growing black holes support this idea, suggesting a shadow population lurking just beyond our sight. The most perplexing clue comes from helium. Quasar spectra show fully ionized helium by roughly 1 billion years after the Big Bang, a feat requiring hard UV photons that only black holes can efficiently produce. Yet the same data reveals regions where hydrogen remained stubbornly neutral long after, as if black holes selectively targeted helium while ignoring hydrogen. Could their radiation have been oddly focused, like a laser beam burning through specific elements while leaving others untouched? Or did their jets create chaotic ionization fronts, leaving patchy remnants of fog in their wake? The feedback loop's true nature might lie in timing. Early black holes may have dominated the initial stages of reionization, their radiation piercing the densest hydrogen clouds. But once galaxies grew numerous enough, their collective starlight might have taken over, finishing the job while black holes shifted to suppressing star formation in overgrown regions. This handoff could explain why the universe's transparency unfolded in fits and starts, a cosmic relay race where the baton passed between rival forces. Until we unravel how black holes balanced creation and destruction in their fiery cores, their role in reionization will remain one of the era's most tantalizing unsolved puzzles. Imagine if the same invisible substance that holds galaxies together also played a secret role in lighting up the cosmos. That's the radical premise behind the dark matter annihilation hypothesis, a daring idea suggesting that colliding particles of dark matter might have unleashed bursts of energy powerful enough to strip electrons from hydrogen atoms during reionization. Forget stars or quasars for a moment. What if the universe's greatest transformation was fueled by something we can't even see? The theory hinges on one audacious assumption: that dark matter isn't entirely inert. Most models treat it as a silent partner in cosmic evolution, its gravitational pull shaping galaxies but otherwise ignoring ordinary matter. Yet if certain dark matter particles were their own antimatter counterparts, they could annihilate upon contact, converting their mass into pure energy. Picture two shadowy particles colliding in the void, vanishing in a flash of gamma rays. A process that, multiplied across billions of collisions, might have flooded the early universe with ionizing radiation. Supporters of this idea point to eerie patterns in modern gamma-ray maps. Telescopes like the Fermi Space Observatory have detected unexplained excesses of gamma rays emanating from galactic centers and dwarf galaxies, regions where dark matter is thought to cluster densely. These faint glows align eerily well with predicted annihilation signals for hypothetical dark matter particles called WIMP, weakly interacting massive particles. If such emissions occurred during cosmic dawn, scaled up by the denser dark matter concentrations of that era, they could have provided the missing energy budget for reionization. But skeptics aren't sold. For one thing, the gamma-ray excesses could just as easily stem from pulsars or other mundane astrophysical sources. More damningly, detailed simulations show that even optimistic annihilation rates would fall far short of the energy needed to ionize the entire universe. Dark matter's distribution was too diffuse, its particles too reluctant to collide, to match the efficiency of starlight or quasars. Unless dark matter behaved wildly differently in the past, its contribution would have been a drop in the cosmic bucket. Then there's the timing problem. Dark matter annihilation would have been most intense in the universe's first 100 million years, when densities were highest. Yet reionization's climax came later, peaking around 500 to 800 million years after the Big Bang. By then, cosmic expansion would have diluted dark matter too much for annihilation to be significant. Unless, that is, something triggered a delayed reaction, perhaps dark matter particles trapped in the gravitational wells of early protogalaxies, where collisions could persist longer. The debate takes a stranger turn with dark stars, hypothetical primordial objects powered not by nuclear fusion but by dark matter annihilation. These bizarre orbs could have glowed steadily for millions of years, their surfaces cool compared to normal stars, but their sheer size making them UV powerhouses. If they existed, their collective radiation might have jump-started reionization before conventional stars took over. The catch: no one's ever found one, and their predicted infrared signatures remain conspicuously absent from JWST deep field images. For now, the dark matter annihilation hypothesis remains on the fringe, a tantalizing what if without conclusive proof. Yet it underscores how much we still don't understand about the invisible 85% of the universe's matter. Whether as a minor contributor or the hidden architect of cosmic dawn, dark matter's potential role in reionization forces us to confront a humbling truth. The story of how light conquered darkness might be stranger than anything we've dared to imagine. Gravity doesn't just bend light, it bends time itself, warping our view of the early universe in ways we're only beginning to untangle. Take the Cosmic Reionization Era. While we piece together its timeline using distant galaxies, some of those galaxies aren't where or when they appear to be. That's the mind-bending effect of gravitational lensing, where massive galaxy clusters act like cosmic magnifying glasses, distorting the light of objects behind them. For reionization researchers, this creates a double-edged sword. On one hand, lensing amplifies faint starlight from the universe's first epochs, letting us peek further back than ever before. On the other, it scrambles the very chronology we're trying to reconstruct, stretching some signals like taffy while compressing others beyond recognition. The most notorious example, a galaxy cluster nicknamed El Gordo, whose immense gravity twists space so severely that background galaxies appear smeared into ghostly arcs. One of those arcs belongs to a galaxy from the reionization era, but thanks to lensing, its light arrives along multiple paths, each taking a different route around the cluster's gravitational well. The result: the same galaxy appears to us at 3 different ages in the same image, like a cosmic time-lapse photo where the subject is caught mid-transformation. For astronomers, this means a single object's reionization signatures, its hydrogen absorption lines, UV emissions, can look like they're from 3 distinct epochs, muddying attempts to pin down when ionization actually occurred. But the distortions get stranger. Some lensed galaxies seem to emit too much ionizing radiation for their place in the reionization timeline, as if their light got stretched to appear older than it is. Others show hydrogen signatures that imply they're younger than surrounding objects, their light path shortened by lensing's funhouse mirror. The James Webb Space Telescope recently spotted a lensed galaxy from just 300 million years after the Big Bang, but its spectrum suggested it had already ionized its local bubble, a feat thought impossible so early. Was this galaxy truly a trailblazer, or had lensing artificially aged its light, fooling us into thinking reionization started sooner? The answer might lie in subtle fingerprints called lensing shear maps. By modeling how a cluster distorts space-time, astronomers can estimate how much it has stretched or compressed background galaxies' light, but even these corrections aren't perfect. Some lensed objects defy explanation, like a reionization era quasar spotted behind the Pandora cluster. Its light curve suggests it flickered over centuries, yet lensing simulations imply we're seeing it sped up by a factor of 10. Its true variability stretched like a record played at the wrong speed. If we misinterpret such quirks, we risk painting a false picture of reionization as a stuttering, uneven process, when in reality, it might have been smooth but for lensing's trickery. Perhaps the greatest irony is that lensing, a tool meant to sharpen our view of the early universe, forces us to question every timeline we reconstruct. As telescopes probe deeper, they'll inevitably find more lensed galaxies from the reionization era, each one a puzzle wrapped in a riddle, a cosmic matryoshka doll where the deeper we look, the more layers of distortion we uncover. And until we untangle gravity's sleight of hand, the true sequence of the universe's awakening will remain tantalizingly just out of reach. Neutrinos are the universe's most elusive particles, ghostly, nearly massless entities that slip through planets like they aren't even there. Billions pass through your body every second, leaving no trace. It's no wonder reionization models often treat them as cosmic wallpaper, background noise in the grand drama of hydrogen's transformation. But what if these spectral particles played a hidden role in shaping the universe's great awakening? Even rare interactions could have tipped the scales in unexpected ways, leaving fingerprints we're only now learning to recognize. Consider this: while neutrinos rarely interact with matter, they do so just often enough to matter in the dense early universe. The hotter, thicker conditions of cosmic dawn meant hydrogen atoms were packed tighter, increasing the odds, however slightly, that a neutrino might nudge an electron, altering its energy state. Individually, these events would be insignificant, but multiply them across the entire observable universe over hundreds of millions of years, and suddenly, these tiny nudges add up to a potential wild card in reionization's physics. One tantalizing clue comes from the cosmic microwave background. Its polarization patterns show faint anomalies, subtle asymmetries that could hint at neutrino interactions during reionization. Some theorists suggest that if neutrinos had even a slight electric dipole moment, a controversial property where these neutral particles act like microscopic magnets, their influence on hydrogen's electrons might have been amplified. Picture a sea of invisible particles subtly tilting the odds, making it marginally easier for UV photons to strip electrons away. Then there's timing. Neutrinos from the Big Bang, cooled by cosmic expansion, would have moved sluggishly by the reionization era. Slow-moving neutrinos are more likely to interact with matter than their high-speed counterparts. If enough lingered in regions where galaxies were forming, their accumulated nudges could have helped clear local hydrogen fog faster than expected, explaining why some pockets of the universe reionized suspiciously early. Of course, skeptics counter that neutrino interactions are so vanishingly rare, their impact would be dwarfed by starlight and quasars, yet nature often hides significance in the marginal. Think of cosmic inflations, quantum fluctuations, once dismissed as unimportant, now recognized as the seeds of all cosmic structure. Could neutrinos be another case where the universe's faintest whispers hold unexpected weight? The most radical possibility: neutrinos might have carried away energy that would otherwise have heated the intergalactic medium. If they scattered frequently enough to transport heat from ionized regions to neutral ones, they could have smoothed out temperature fluctuations, subtly guiding where and how reionization progressed. It's a long shot, but in an era where so much remains unexplained, even ghost particles deserve their day in the cosmic courtroom. Until we build detectors sensitive enough to probe these ancient neutrino whispers, their role in the universe's first light will remain one of reionization's quietest, most tantalizing maybes. Plasma, the fourth state of matter, is notorious for its unpredictability. In labs around the world, physicists have watched it twist, snap, and erupt into turbulent instabilities without warning. Now, those same chaotic behaviors might hold the key to one of reionization's most stubborn mysteries: why the universe's great ionization unfolded in such a lopsided patchwork fashion. The clues first emerged in fusion reactors, where physicists struggle to contain superheated plasma in magnetic fields. Despite precise control, the plasma often fractures into filaments or swirls into violent vortices, defying expectations. These instabilities aren't just laboratory curiosities, they're governed by universal laws of electromagnetism and fluid dynamics, laws that would have applied just as fiercely to the ionized bubbles of the early cosmos. So what if reionization wasn't a steady march toward transparency, but a fireworks show of plasma turbulence, with ionization fronts surging and collapsing like waves in a storm? This idea turns conventional models on their head. Most simulations treat reionization as a smooth, expanding wave, like ink dispersing in water, but plasma instabilities suggest a far messier reality. Imagine a galaxy's UV radiation flooding into surrounding hydrogen, ionizing it into a plasma bubble. At first, the bubble grows evenly until tiny fluctuations in density or magnetic fields trigger a runaway instability. The bubble's edge might ripple, fracture, or even recoil, leaving behind pockets of stubbornly neutral gas. In lab experiments, similar instabilities create fractal-like patterns, with ionized and neutral regions tangled like lace. Could the universe's patchy reionization be the cosmic-scale echo of this same chaos? Support for this wild idea comes from the Lyman alpha forest, the intricate web of hydrogen absorption lines in quasar light. Some of its tangled structures resemble the fractal edges seen in lab plasmas, far more than the clean boundaries predicted by traditional models. Even more telling are the void regions, vast expanses where reionization happened suspiciously fast. Plasma instabilities could explain these outliers. If an ionization front hit a region of lower density, it might accelerate unpredictably, like a flame racing through dry grass. Conversely, denser filaments could have resisted ionization longer, their plasma collapsing back into neutrality like a deflating balloon. There's a twist, though. Space isn't a lab, and the early universe had variables no experiment can replicate. Primordial magnetic fields, weak but pervasive, might have guided plasma instabilities in ways we can't yet simulate. Dark matter's gravity could have tugged at ionized gas, distorting instability patterns. Even the quantum noise of the first photons sputtering into existence might have seeded fluctuations that snowballed into full-blown turbulence. The implications are staggering. If plasma instabilities shaped reionization, it means the universe's transformation wasn't just driven by stars and galaxies. It was choreographed by the quirks of physics at its most chaotic. And that raises an even deeper question. Could these same instabilities have left behind cosmic scars, hidden in the distribution of galaxies we see today? The answer might lie in next-generation telescopes, built not just to observe the cosmos, but to listen for the echoes of its ancient turbulence. At the heart of reionization's chaotic patchwork lies a staggering connection, a thread stretching all the way back to the universe's first trillionth of a second. Those uneven ionization bubbles, the stubborn pockets of lingering hydrogen fog, even the strangely clustered galaxies, they might all trace their origins to quantum fluctuations, microscopic ripples in spacetime itself during the Big Bang. What began as subatomic tremors in the newborn cosmos eventually snowballed into the vast cosmic structures that shaped reionization's uneven dance of light and shadow. Consider those first quantum ripples, random flickers of energy so tiny they'd make atoms look like giants. Inflation, the universe's explosive early growth spurt, stretched these quantum quirks across cosmic scales, embedding them like invisible blueprints in the fabric of space. Fast forward hundreds of millions of years, and those same fluctuations dictated where matter clumped into the first galaxies and where voids stretched empty. Denser regions became star factories, their radiation ionizing surrounding hydrogen faster, while sparser zones lagged behind. It's like blowing soap bubbles. The initial breath's subtle variations determine whether you get a perfect sphere or a lopsided cluster. The evidence is etched across the sky. Maps of the cosmic microwave background reveal temperature variations, slightly hotter and colder patches that align eerily with later ionization patterns. Those subtle differences, just one part in 100,000, mirror the distribution of galaxies during reionization, as if the universe remembered its quantum beginnings. Even the largest ionized voids, some spanning hundreds of millions of light-years, might simply be grown-up versions of primordial underdense regions, their gas too thinly spread for stars to ignite quickly. But here's where quantum mechanics meets cosmic irony. The very randomness of those early fluctuations created structure. Without them, matter might have spread perfectly evenly, leaving no seeds for galaxies and no uneven ionization fronts. Reionization's patchiness isn't a bug. It's a feature written into the universe's code from the very first moment. Yet mysteries linger. some ionization bubbles grew far larger than standard quantum inflation models predict, while certain dense galaxy clusters show oddly aligned shapes as if sculpted by forces beyond mere randomness. Could there have been exotic quantum effects, fields, or particles we haven't discovered that left extra fingerprints on the early universe? Or perhaps gravity, weaving its magic over eons, amplified certain fluctuations in ways we're only starting to model. The most profound implication is this: reionization wasn't just a chapter in cosmic history, it was the universe finally revealing the quantum handwriting of its birth. Every ionized bubble, every stubborn wisp of hydrogen fog, carries echoes of a time before time, when the largest structures in existence were smaller than a proton. And as we trace those echoes backward, we're not just solving the mystery of how light conquered darkness, we're reading the very first lines of the universe's autobiography. We think of reionization as a cosmic curtain lifting a single, decisive moment when the universe became transparent. But what if the curtain never fully rose? Hidden in the darkest corners of space, patches of stubborn hydrogen clung to neutrality, surviving for billions of years after the rest of the cosmos had blazed into light. These cosmic holdouts, lurking in vast voids between galaxies, challenge everything we thought we knew about reionization's grand finale. Take the Leo cloud, a massive pocket of neutral hydrogen discovered just 500 million light-years from Earth, a stone's throw by cosmic standards. Spectroscopy reveals it's barely ionized, as if time forgot this corner of the universe. How could such a relic persist in a cosmos flooded with starlight? The answer lies in the voids immense, near empty regions where galaxies are so sparse, their collective radiation never reached the gas drifting between them. Picture a desert so vast, even sunlight struggles to cross it. These voids became neutrality's last refuge, their hydrogen untouched because there simply weren't enough stars nearby to rip its electrons away. But here's the twist: some of these neutral pockets should have been ionized. The Smith Cloud, another hydrogen relic floating near the Milky Way, is surrounded by galaxies whose radiation ought to have reached it eons ago. Yet it remains stubbornly unchanged, like a snowbank refusing to melt in summer. The leading theory, magnetic fields, strong primordial fields, could have acted as force fields, deflecting ionizing photons or trapping the gas in cool, dense clumps resistant to radiation. It's as if these clouds wore cosmic sunscreen, shielding themselves from the universe's ultraviolet onslaught. Even more puzzling are the Lyman alpha ghosts, faint absorption lines in quasar light suggesting neutral hydrogen lingered in some regions until as recently as 2 billion years ago. That's halfway to the present day. These ghosts haunt the data, hinting that reionization didn't so much end as fade unevenly into the background, with islands of fog surviving long after the cosmic seas had cleared. The implications are profound. If neutrality held out in patches, the universe's transparency was more like frosted glass, letting light through but with lingering imperfections. And that changes how we interpret everything from galaxy formation to the cosmic microwave background. Maybe the universe's great awakening wasn't a sunrise, but a slow, uneven dawn, with shadows clinging where the light hadn't yet reached. And if we listen closely, those shadows might still whisper secrets about how darkness fought its last, lonely battles against the light. 25 mysteries, each one a thread in the grand tapestry of the Cosmic Reionization Era, and yet, even now, they weave a story far from finished. What we've uncovered isn't a tidy timeline, but a cosmic detective story, filled with contradictions, missing pieces, and clues that refuse to fit. From phantom quasars that shouldn't exist to the eerie whispers of hydrogen clinging to neutrality billions of years too late, every discovery peels back another layer, revealing just how little we truly understand about the universe's fiery transition from darkness to light. The beauty of these mysteries isn't just in their complexity, it's in what they promise for the future. Upcoming missions like the Nancy Grace Roman Space Telescope, with its staggering field of view, could finally spot those elusive early galaxies hiding in the shadows. Next-generation radio arrays might untangle the 21-centimeter signals riddles, while advanced spectrographs could decode the cosmic infrared background's hidden messages. Each tool is a new lens offering fresh ways to interrogate the past, and with every answer, we're not just solving puzzles, we're rewriting the origin story of everything we see. But here's the most thrilling part. You're witnessing this detective story unfold in real time. The next breakthrough could come tomorrow, flipping our understanding on its head. Maybe it'll be dark matter's role finally confirmed, or perhaps the James Webb Space Telescope will stumble upon a population 3-star frozen in time. Whatever it is, one thing's certain: the Cosmic Reionization Era isn't just ancient history. It's a living mystery, and we're all part of solving it. So, which of these 25 mysteries grabs you the most? Is it the missing galaxies, the phantom quasars, or the ghostly hydrogen holdouts? Drop your thoughts in the comments. Let's geek out over the universe's greatest unsolved case together. After all, the next clue could come from anywhere, even you.